Welcome to Data Mining, Lecture 6, Part 2. In this part, we will focus on text mining. In particular, we will focus on the text association rule mining. Then in Lecture 6, Part 3, we will talk about trend detection and event detection in text databases. In Lecture 6, Part 1, our focus was on review of text retrieval or information retrieval. Okay, and there were two most important measures for evaluating the performance of text retrieval systems, and those two measures are recall and precision. And these two are very important, and I have to point out that this might appear in your exams about their definitions, about their meanings. Text mining is different from text retrieval in the sense that for the text retrieval, what you do is you are given a query, which basically is a combination of keywords. Okay, and then the system, based on the query, which is a collection of keywords, will search the underlying database, and then we'll find documents that contain those keywords. So that's retrieval part. The system is given keyword or query, okay, and the system, based on the query, the system does search. Text mining, on the other hand, is very much like relational or transactional database mining, where the engine tries to discover association rules or patterns from the text databases. So normally what you are given with is a set of parameter values, such as support, such as confidence, and that's all. You're not given with a query. Okay, so there's no notion of query here. The system is given a set of parameter values, such as support, confidence, and then the system will generate candidate patterns, and then will verify whether these candidate patterns satisfy the user-specified parameter values. So this computing structure or computing paradigm is very different from traditional query engines or search engines. So that's the main difference between mining and the search. For the search, the system is given a query. Okay, the query is clearly specified. For the mining, the system has to generate candidate patterns and then test to see whether these patterns satisfy some user-provided parameter values. And you can see easily that mining is more computing intensive because mining needs more resources to do generation and to do the testing. There are many types of text mining. Keyword-based association analysis. We will give a particular example to illustrate an algorithm for keyword-based association analysis at the end of this part. Document classification. You are given several classes of documents, okay? And then for a new document, you try to assign this new document to one of these classes. Okay, so you start with several document classes, okay? And then for any new document that is submitted, you try to assign a new document to one of these classes. Clustering. You have a lot of documents at hand right now. Here, the documents could be email messages, could be web pages written by HTML, could be XML pages. Okay, XML databases are right now hottest databases that database people are dealing with. And you try to cluster these documents based on different criteria. For example, you can group documents based on who write those documents. So if these papers are written by Professor X, you put them in the group X. If these papers are written by Professor Y, you put those papers in group Y, and so on. So that's one way to cluster documents. You could also cluster documents containing information from a common source. For example, if these papers are published in the ACM SIGAMO conference or conferences, you assign these papers to a group containing all the SIGAMO papers. If these papers are published in the very large database conferences, you assign these papers to another different group called the VidoDB. If these papers are published in the SIGA KDD Data Mining and Knowledge Discovery conferences, you assign these papers to that group. So you can cluster documents based on where they are published. So this type of classification and clustering algorithms are very popular and are very useful. Even today, we are working on this classification and clustering algorithms almost on a daily basis. In the sense that my students have a lot of data, and I ask the students to try to cluster the data based on some similarity or dissimilarity measures. For example, right now we have a bunch of metabolic pathways obtained from Dubon chemical company, and we represent these pathways by trees, and then we develop a distance for trees, and then we cluster these pathways based on the distances we have developed. And this becomes research, because first, representing pathways by trees is a novel idea, and there are few schemes that are used to do this kind of transformation. Second, once you have the trees, then you try to develop new distance measures to measure the distance between trees. And measuring the distance between trees is a non-trivial problem. It's a very difficult problem. You can look at my website. Under the publication, you can find papers relevant to tree matching or distances between trees. And if you look at papers, you see these materials are very difficult materials. Third, you publish this distance or you develop these distances. But many of these distances might not make sense in a domain. For example, right now we develop this topological distance for trees. But then we have to submit these distance values. We use the algorithm, we calculate these distance values. And then we submit these distance values to domain scientists, to a biologist in Dubon. But then he says that this distance might not make sense in their domain. So we have to modify these distances. And the modification itself is non-trivial as well. So this whole process then is known as research. You start with data. Metabolic pathways. Data are very difficult to process. So you transform the data to something that is easier to process. For example, trees. And then you deal with trees. You develop a new distance measure for trees, for measuring the distance or similarity between trees. But then your distance measure might not make sense in domain. So you check with the domain scientist. And domain science gives you feedback, saying that perhaps you try that. You have to, for these two trees, you have to somehow, give me this distance value rather than that distance value from your algorithm. Then you go back to modify your algorithm. Or perhaps you develop another new algorithm. So we put this flow chart, this diagram, in our proposal in the early 1990. to try to define the general diagram or general flow chart for, for data mining or for, pattern discovery in scientific databases. And that proposal was funded by National Science Foundation. Because this diagram, actually, just almost 10 years ago, we were able to categorize what will happen in scientific data mining. And this is the actual process. Right now, today, I'm dealing with this. Okay, we go through these processes. We check with the scientist. We get feedback. We modify this distant algorithm, and therefore the clustering algorithm or classification algorithm. So this data mining process is very common, and that appears in almost every scientific domain. Okay, in your earth science, biological science, and so on. And similarly, in text mining, you see the similar scenario. Okay, you try to classify or cluster documents. You need to have distant measure to measure the similarities between these documents. As I mentioned last time, one very commonly used distant measure is to represent documents by vectors, and then use a cosine similarity or cosine function to measure the distance between vectors. So if you look at these processes, you see that all these processes share a common framework. Okay? What is this common framework? You have original objects. In this case, documents. Documents are too difficult to process. You look at your lecture notes. It's a huge book. It's very difficult to process unless you use the natural language processing techniques. But the many natural language processing techniques are still not mature. Okay? We claim that, or the natural language processing people claim that they can develop techniques to fully understand what is written in this book. Okay, is that claim true? Or, that claim would be, it's very difficult to accomplish that claim. The main reason is that text understanding depends on very much the context, and depends very much on the terms used in the book and so on. So what the people do is then to represent this text or this lecture notes, this 400 pages notes, by a vector, by a Euclidean vector. Okay? Now, how to represent a book by a vector, I have already explained to you last time. What we do is we use some techniques to remove unimportant words in a book, such as articles, such as prepositions, such as those commonly occurring while they don't have, much meanings. So you remove a lot of such words from your book. And then you identify, for example, 200 keywords in your book. You look at this 400 pages lecture notes. What are keywords then? What are keywords in the lecture notes? Mining is one keyword. Text is another keyword. Clustering is a keyword. Classification is a keyword. Association is a keyword, and so on. So these are keywords. So normally, depending on the domain, you can identify, for example, 1,000 keywords, or you predefine these keywords, or use some pre-processing techniques to get these keywords from the documents you are processing. Okay? Let us say that finally you identify or you predefine 1,000 keywords, and you have a bunch of documents at hand. Then you use a Boolean model to represent each document. What is a Boolean model? This model has been published in Information Retrieval long ago, 30 years ago. A very old idea. You have 1,000 keywords, and you have a book. So you look at the book. So suppose you sort these keywords in lexicographical order. And look at the book. Look at the first keyword, clustering. Does this book have the keyword clustering or not? Yes or no? If yes, you put a 1 there. If no, you put a 0. So let us say that the first position in this vector corresponds to the keyword clustering. All right? And the second position corresponds to the keyword classification, and so on. You sort these keywords, and therefore you can say position 1, position 2, position 3, and so on until position 1,000. Then you look at this book. Position 1 corresponds to clustering keyword, the keyword clustering. So you look at the book, you check to see whether the book contains the keyword clustering or not. If yes, you put a 1. If no, you put a 0. So this is what we call a Boolean model, because you either have 0 or 1 value. Okay? Then you look at the second position in this vector. The second position in this vector corresponds to the keyword classification. Then you look at the book to see whether the book contains the keyword classification or not. If yes, you put a 1 there. If no, you put a 0. And so on and so on. Okay? So, at the end, you can represent this book by a 1,000 dimensional vector whose value, look at this vector, then in the vector, the values are either 0 or 1, 1, 0, 1, 0, 1, and so on. This is the simplest model called the Boolean model. Of course, you could use other weighted models. For example, if this keyword clustering appears many, many times, you calculate the number of occurrences in that book. If it occurs a lot of times, you give more weight in that position. And this is called a weighted model. So in each position in the vector, instead of having 1, 0 value, you have a real number there. That indicates the weight of this keyword in that book. And so I normally just suggest you to use the Boolean model because it's simple. How many of you have heard the Boolean model and weighted models? Raise your hands, please. So that's why, because they are new to you, so I suggest you to use the simple model first in your implementation of your project. And in future, you can you can adapt more difficult models. Because these materials are new to you, there is no point to start with difficult things. Okay, what you should do is you start with simple things first. Okay, this is always my philosophy of teaching. We can teach you a lot of difficult materials, but if none of you can understand these materials, the effect is 0. That's not worthwhile. A waste your time and my time. All right. So what we hope to do is to teach you some simple materials. And once you are familiar with the simple materials, we can look into more difficult materials. The topic itself is very involved, very complicated. As I said, there's so many conferences are ongoing, and each conference has so many papers, so many researchers in the world, so many PhDs, so many professors, so many scientists are working on publishing papers days and nights. So it's very difficult to understand so many materials at one time. What we do, or what we hope to do, is to start with simple things. And after you understand the simple things, we move on to more difficult things. Just like my homework. Are the homework simple enough, or they are too difficult for you?
This took a lot of time.
Huh?
This took a lot of time.
Is it simple or difficult?
It's simple, but it takes time.
That's a key point. That's why it's called the exercise. You are in the beginning phase of in the data mining. You practice, you exercise, and then you spend time. But after you spend your time, the material is in your mind. You will never forget that. You will never forget the ID3 algorithm in the future. And that algorithm is very important. ID3 algorithm or C4.5 algorithm have been used in the machine learning field for many, many years. I went to the conferences, 1997, I think, to AI conference, which is the best conference in AI, in Portland. That's in the city center in Portland. And I was in their talk. At that time, the inventor of this ID3 algorithm, Professor Quinlan, was there. And he presented a paper, and I was just sitting behind him. And that year was 1997. And Quinlan invented this ID3 algorithm, which you exercise almost 25 years ago, long ago, when you were a child. Maybe some of you were not born yet. The algorithm was there, okay? But interesting enough, presenters from MIT or from Stanford still cite his paper, and they give a lot of credits to Quinlan, who sat on a chair in the first row. And many algorithms, even today, published today, actually are extensions of this ID3 or C4.5 algorithm. So they still talk about extensions. There was no new invention anymore. Just extensions. They extended this algorithm to deal with more sophisticated cases. Okay. So that's why this algorithm is so important. So many applications and so many efforts have been put in the last 20 years. Trying to improve this algorithm. 20 years are very long. Many of you were still born, were a child, and now you are adult. So it's not a short time period, 20 or 30 years. And the researchers have done, they work hard, days and nights in these 20, 30 years to try to develop new things. But if you look at the new things, many of them are still based on ID3 or C4.5 algorithms. So that's why this algorithm is so important. Okay. The text mining, on the other hand, is a relatively new field. But if you actually look at these materials inside this field, we borrow a lot of old ideas from the literature and just try to modify them and then adapt them to this new field. Many of these ideas are not that new, and actually many of them share previous published algorithmic ideas. Just in a few transparencies, I'm going to talk about this keyword-based association analysis. That's almost exactly the same as transaction association rule analysis. Very similar, just like your homework 1. Okay, but the term is different now. We use a text mining rather than the transactional data mining. But the ideas are basically the same. Link analysis. On the World Wide Web, you have a lot of links, right? Each hyperlink can be represented as an edge in the graph. Okay, many people model this World Wide Web as a graph. If there's a link from this website, which is a node in the graph, to that website, then we put an edge from this node to that node. Okay, so that's a link. And a lot of research has been done to try to analyze links on the World Wide Web, try to find unusual correlations between entities. Sequence analysis. If you look at text, look at a book. A book is composed of sequences or strings, right? I have a dream. The dream is blah 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 and so on. So that's a string. That is composed of English characters. So a lot of sequence analysis algorithms are being applied to predicting a recurring event in text. Okay, so text mining actually borrows a lot of string searching algorithms. Okay, and many algorithm people have published string searching algorithms in the last 30 or 40 years, and we borrow a lot of their algorithms to try to, apply them to text mining. Anomaly detection. We try to find information that violates usual patterns. Outlier is also an anomaly. Okay. Hypertext analysis. Here you try to discover patterns embedded in anchors and links and so on. So we will look at each of these items in detail in the next few transparencies. Keyword-based association analysis. As I stated earlier, you have a collection of documents and you try to discover associations between keywords in these documents. What you do is you predefine, say, 1,000 most important keywords, 1,000 for example. And then for each document, you represent that document as a 1,000 dimensional vector. At each position, depending on whether that document has that keyword or not, you can put it 1 or 0 in that position. Okay? And then you can use association rule analysis algorithms to find the relationships between these vectors. So how to identify keywords? You pre-process the text data by parsing, stemming, removing stop words, and so on. Okay? So we will look at a particular example that shows how keyword-based association analysis is done. Document classification. If you look at these data mining algorithms, you will observe that one most important thing, in fact, is to try to identify or try to measure the similarities or dissimilarities between documents. Once you have the similarities values or dissimilarity values or distant values between documents, you can apply k-means algorithm, for example, to cluster documents. You can apply nearest neighbor classifier to classify documents. Remember the nearest neighbor classifier? How many of you forget the nearest neighbor class file? What is the nearest neighbor class file? You have a lot of classes in there, right? Now you have a new object or a new document. So where this document should go, you assign the document to the class that contains the nearest document of this given document. That's the nearest neighbor class file. Now once again, we touch on the notion of nearest. How to define nearest? So that's basically it's based on a distance, right? We are close and we are far away from each other. So the distance measure is a key idea in data mining. We have to understand how to evaluate the distance between, for example, Zhang Hui and I, and then we have to evaluate the distance between me and Tony. And once you have these distance values, you are able to use previous algorithms, like a nearest neighbor classification algorithms, k-means algorithms, and so on, to cluster or to classify these objects. So the bottom line is how to calculate the distance between objects, how to calculate the distance between me and Zhang Hui, how to calculate the distance between me and Tony, and so on. So that's a key idea that you should observe. In real life, this is also true. When you try to apply these classification algorithms or cluster algorithms to the real life applications or real life problems, you have to understand first what data objects you are dealing with. You are dealing with metabolic pathways, or you are dealing with computer-aided design, computer-aided manufacturing parts, or you are dealing with human objects, or you are dealing with what? You have to understand the data objects at your hand. Second, once you understand the data objects, for example, we are dealing with human objects. How to cluster human beings? It's a little bit difficult, right? Because this is an abstract notion, right? So what we can do is to represent each human being by a set of attributes. For example, this person has gender. This person has the education level, has a degree. This person has, salary, income. But this person was born in this country, was born in other countries, and so you can identify a bunch of attributes. Okay, then you model each data object by, for example, a record of attributes or a tuple of attributes. So now this is a transformation process. You transform raw data, original data, to some data objects you are able to handle. What type of data objects computer can handle normally? Computer can handle strings. Computer can handle points. And these are common data types you use in your Pascal programs or in your C programs, right? Your program can handle vectors. Your program can handle tree structures. Your program can handle graph objects. What your program cannot handle is, for example, a human object. What your program cannot handle is, for example, a regional protein structure, because they are too sophisticated or they are too abstract. So what we do is we transform this original data to data types our programs or our algorithms can manipulate. And if you look at Pascal or C language, how many of you know Pascal right now? Raise your hands, please. You don't care Pascal anymore? 15 years ago, when I first, came to the countries to study computer science, I was in mathematics department before I came here. All of us must learn Pascal. As it was, we learn Pascal all the times. Now and then in the end of 1980, I think people gradually switched to C and so on. Am I right? Now today everybody is talking about Java. Nobody cares Pascal or C, C++, and so. So that's this is evolution. Okay, but anyway, look at your Java program or look at your C program. You can declare data types like string types. You can deal with vectors or points. You can deal with strings. You can deal with these data types. You cannot deal with other kind of abstract data types, more abstract data types like CAD/CAM parts, tables, chairs, human beings, and so on. So how to deal with these objects? You do the transformation. You transform or you represent these objects by data types in your programs. And common data types include vectors, strings, trees, and so on. Okay? Is that clear? So the first step is to do transformation. Okay, that's so once you have done this, now you end up with data types that your algorithm or your program can handle. You can declare this data type in your Java program. Okay, suppose your manager asks you to do clustering. Cluster these data objects. In order to do clustering, the next step is to try to develop a distance measure to measure the similarities between these data types now you have. Okay, the strings or points or vectors and so on. If they are vectors, you can use Euclidean distances. If they are strings, you can use string eddy distances to measure the distance, and so on. Now, once you have the distance values, then you can do the clustering. You can just borrow the k-means algorithm immediately to do the clustering. You can use agglomerative algorithm to do the clustering, and so on. That clustering only needs the distance between objects, period. That's all. So, similarly, for documents, we cannot deal with a book. A book is too large to process. So what we do is we transform book into a vector, into, for example, a one-dimensional vector. And then we have a lot of algorithms dealing with vectors, right? We have Euclidean distances for measuring the distance between vectors. We can use cosine distance to measure the distance between vectors and so on. There are many, many distance measures. Okay? And then, so that's the whole idea. Okay? Text document classification differs from the classification of relational data. For the relational data, the data type is a record or a tuple of attributes, right? You have an attribute and attribute values. And for text, like a book, this data type is different from records. So we have to change our classification algorithm slightly to this new domain. But the changes are actually, to me, are not that significant. Okay. In fact, if you look at a lot of these text mining papers or document classification papers, many of them actually are based on the existing algorithms or ideas, and they do some minor modifications. So this is another technique to do document classification. Okay, you can extract keywords or terms using the traditional information retrieval techniques. Okay, and then you organize these keywords into a hierarchy. Okay, and this hierarchy, actually, if you go to the Google, you can find the most important hierarchy or most widely usable hierarchy. Widely used hierarchy, which is called the WordNet. WordNet seems to be developed at Princeton. I forgot the original place, but if you go to Google, you can find this WordNet hierarchy. This is very much like a thesaurus, in which the keywords are organized into concept hierarchies. Okay, for example, dolphin is an animal, and a dolphin is a mammal. Mammal is an animal, and so on. Okay, this kind of concept hierarchy. Okay, and then you can use this concept hierarchy to try to do the classification. At the end of the semester, we will give a particular classification algorithm that basically is based on concept hierarchies to do classification. Concept hierarchy basically is very much like is a hierarchy in your ER diagrams. Okay, is a hierarchy. So that's here's another technique to do classification. We can use association rules between keywords to try to do document classification. Suppose you have 5 classes of documents. Okay? So for example, this class of documents talk about sports, and this class of documents talks about hobbies, and that class of documents talks about like computer, PC, and so on. So you have different classes of magazines or documents. Each class talks about different subjects. And you try to find representative keywords for each class. So you look at the class of documents or magazines that basically are concerned with sports. And then you do the association analysis. You try to find associations between keywords in these documents. Okay? So for example, one association may be basketball implies Jordan. That's just one example of association. We will talk about particularly this association rule discovery algorithm. But in essence, this is very much like a transactional database, association rule discovery algorithm, where you have a lot of transactions, item sets, and you discover associations between items. Here, we discover associations between keywords. We have a lot of keyword sets. Okay, so you discover associations. Okay, in this class of documents, we observe that when basketball is mentioned, then Michael Jordan is also mentioned, or when basketball is mentioned, Kobe Bryant is mentioned. So we discover those associations. We also discover that when, for example, in football is mentioned and a particular person is mentioned, so you discover these associations. Okay, then these associations or the relevant keywords can be used to represent this particular class of magazines. When there's a new magazine submitted and you try to assign this new magazine to one of these classes, okay, then what you do is you look at these keywords in this new magazine to see whether there's important keywords appear in this sport documents or the sport magazines, whether their keywords coincide with each other. If that's the case, you assign this magazine or this new document to that particular class of documents. Or otherwise, you look at another class of documents to see whether this new document contains keywords coinciding with the keywords representing that class of documents, and so on. Now, how do you detect these representative keywords for each class? Use the keyword association rule analysis. You try to discover some associations in that class of documents. You try to discover associations between keywords, and you look at those keywords. Those keywords become important keywords if they appear in high support, high confidence associations. So that means those keywords are significant. Okay? So that's another way to classify documents, by looking at the keywords and by looking at the association rules for each class of documents. So so far you have learned several techniques for classifying documents. You can represent documents by vectors, and then you use nearest neighbor classifier to classify documents, right? You can represent each class of documents by representative keywords. Now, how to discover these keywords? You try to apply this keyword or this keyword association mining algorithm to discover important association rules between keywords in this class of documents. And those keywords become representative keywords if they appear in a high support association rules or high confidence association rules. Okay. Then for new document, you look at the keywords inside and you see how these keywords match with those representative keywords for different class of documents, and use those keywords matchings to determine where this new document should be assigned to. Any question about these classification algorithms? So there are different types of classification algorithms. Okay? Clustering. Well, the simplest way perhaps is to represent a document by vector, and then you use the cosine distance to measure the distance between vectors, and then use K-means algorithm to do the document clustering. And I mentioned to you last time about cosine similarity between documents. What is a cosine similarity? This is a very commonly used similarity between documents. You represent each document by a vector. And let me take a very extreme example. Suppose each document is represented by a two-dimensional vector. Two-dimensional vector. So that means we only look at the keywords, two keywords, okay? So suppose I look at only the keywords knowledge and data. So I look at this book. First, I check whether this book has a knowledge or not, has a keyword knowledge or not. Check the whole book. If there's a knowledge there, if the keyword knowledge appears in the book, so I put it at first position 1. If the keyword knowledge doesn't appear in the entire book, I put a 0 there, indicating that this book doesn't contain a keyword knowledge. That's X coordinate. Then I look at the Y coordinate. This time I check the keyword data. I check the same book to see whether the keyword data appears in the book or not. If it's there, Y coordinate is 1. If it's not there, Y coordinate is 0. So this document now is transformed to a two-dimensional vector. And depending on whether that contains the keyword knowledge and the data, I put a 1 or 0, I put a 1, 1 or 0, 0 in that vector. Now suppose I have another book. I do the similar transformation. I check to see whether this book has a keyword knowledge or whether this book has a keyword data. Okay, let us look at a very extreme case. When I give examples, I always want to use extreme cases to try to motivate you. Suppose this book has knowledge, so you put a 1 in the X coordinate, but it doesn't have the keyword data, so you have 1, 0. So this book is represented by 1, 0. On the other hand, this book doesn't have the knowledge keyword, but have the data keyword. So this book is represented by the vector 0, 1. So this is 1, 0. This is 0, 1. Is that clear to you? 1, 0, 0, 1. So you calculate the cosine function, cosine value for these two vectors. What is a cosine? So these two are actually orthogonal to each other, right? So the cosine distance for these two vectors is what? 0, right? You take the inner product of 1, 0 and 0, 1. The numerator is 0. So that means these two documents are completely different to each other, which is true because this has a keyword knowledge but doesn't have the data. This has data but doesn't have the knowledge. So they are completely different. They talk about completely different things. Okay? On the other hand, suppose this book has a keyword knowledge and doesn't have the data keyword. This has a knowledge keyword, doesn't have the data. So they both are represented by the vector 1, 0. And when you take the cosine value of these two, they are overlap. They are overlap with each other. So their similarity, their distant value is what? 1. Meaning that they are entirely the same. That's right. Because both books touch on the keyword knowledge and they don't have the keyword data. And therefore, they are completely the same. In terms of keyword representations, they are completely the same. Okay, that's why cosine similarities make sense in document processing. Okay, so that's why cosine similarity is one of the most commonly used similarity measures in document processing. And once you have that similarity measure, you can do document clustering. So actually the important thing is, Dr. Wayne, how do you identify or predefine these 1,000 keywords for representing this collection of documents? How do you realize that you have these 1,000 keywords? That's also your homework in your implementation project 3, okay, that you are going to implement at the end of this lecture. So you have to use procedures to remove stop words, stem processing, and so on. And then you recognize important keywords from these documents at your hand. Okay, you have to do some pre-processing. And I give you a hint. If you go to the library and you check out any book whose title has to do with information retrieval, pick up the book. You can find a lot of algorithms described in a book about keyword identifications. And there, they use the term document indexing. This term is overloaded, by the way. Document indexing. We also learned document indexing here, but when we talk about document indexing, what we mean is that we create an inverted file for a document, for indexing a document. Just like in your book, at the end you have the index, right? That's an inverted file. That's what we mean by index. By looking at a particular word there, you can find the corresponding pages in which that word occurs. So you can go to those pages to find that word, right? Look at the index of each book. And that index is called an inverted file. Okay? That's what we mean by indexing a document. That is, you create an inverted file or signature file for a document so that if you want to locate a particular keyword, you can find that keyword quickly. Just like for B-tree, for relational databases, you create B-tree on the database, and if you want to find a particular record based on the B-tree, you can find that record quickly. If you want to find the record John Smith, you can look at the name attribute. Suppose there's a B-tree on the name attribute, you can find the record with John Smith quickly in your database. So you always count on data structures such as B-trees, such as inverted files to do quick processing. Okay? Now, here, so that's what we mean by document indexing or indexing a document. But then in IR, they overload this term document indexing. If you look at the IR books, one way to interpret document indexing is that given a document, you try to identify keywords in that document. How many keywords that document has? How to pick up those keywords? Which words can be treated as a key? Which words can be treated as keywords? And so on. And this procedure is known also as document indexing. You know, you identify keywords from a particular document. A document might be huge. Look at this lecture notes. It has 400 pages. How do you define which words should be keywords and which should not be keywords? It's not a trivial process. Okay, in particular, if this one is digitized in computer, you need to write a program to scan this 400 pages lecture notes to try to identify keywords, to do document indexing, to identify those important words in this document. Okay? And that process has been done already. Okay? The technology is very mature. So you look at the information retrieval books, you can find different algorithms to remove stop words, stem analysis, and so on. And finally, you are able to find a bunch of keywords representing that document. Any questions so far? Raise your hands, please. And that will be in your next implementation project. And as you will see, you are going to extract HTML pages from the website, and you are going to identify keywords in those HTML pages, and then use the represent each HTML page by a keyword vector. Okay, so there are three particularly interesting and important text mining processes. Okay, and by definition, text mining is to find or to discover knowledge in textual information. In this part 2, we will focus on association discovery. We try to find correlations or associations among keywords in a set of documents. In the next part 3, we will focus on trend discovery and event discovery. Well, these terms are very new to us. It's pretty interesting term. But once you look at the algorithms, you see that the algorithms actually are based on previous techniques. Okay, it's not that difficult. So web text mining. Now, so you have text mining, but if your text is restricted to web pages like HTML documents and so on the websites, then that becomes web text mining. So for web text mining, you try to search through HTML pages or unstructured data on the web, on the internet, and try to derive meaning or try to find associations or try to do clustering or classification on the World Wide Web. And that big area is called web text mining. Now, of course, on the web, you have not only text, but also multimedia formats like a GIF file, JPG files, and sound, voices, and so on. So the subject is far more sophisticated than just text or web text mining, okay? But text mining is always an interesting subject because most of the data you are dealing with still have the text format. Email messages, the text, HTML pages, large portion of HTML pages are still based on text and so on, okay? So we'll look at the association discovery between keywords in text. And then in the next part, we will then focus on trend discovery and event discovery. Everything here is essentially similar to your homework 1, transactional database association discovery. Okay? In homework 1 or in the transactional database association discovery, you focus on the so-called item sets. Okay? Where each transaction is a collection of items. And then what you do is you try to discover associations between items purchased by these transactions in your database. Okay? And what you do is use a priori algorithm to discover associations between items. That's a whole story about your transactional database association transactional association discovery. Similarly here, we try to discover associations between keywords. Here, just like transactional databases where each transaction is represented by a collection of items, here, each document is represented by a collection of keywords. And we have already repeated this many, many times, right? You all know how to represent a document by a collection of keywords. And this process is called document indexing. Okay? So each document is represented by a collection of keywords. So you have a bunch of keywords. And then you generate the so-called keyword sets. 1 keyword set, 2 keyword sets, 3 keyword sets, and so on. 1 keyword set contains only 1 keyword. 2 keyword sets containing 2 keywords. 3 keyword sets containing 3 keywords, and so on. And then from these promising keyword sets, you try to discover associations from those promising keyword sets. So for example, for a particular rule, X determine Y or X implying Y, you have support and confidence. Now here, we define the support for the rule X implying Y to be the number of documents in this collection of documents that contain both X and Y, where X is a set of keywords and Y is another set of keywords. Just like your transactional database association where you have X implying Y and your X is an item set and your Y is another item set. For example, X is bread, Y is butter. X is soda, Y is wine, and so on. Bread implies soda, and so on, right? That's what you have in your homework 1. Here, we change this, okay? X represents a keyword in a document. For example, X is Jordan. Jordan implies basketball, or basketball implies Jordan. Okay, so that's the only thing we change. The whole algorithm is the same. Now here, this is a little bit different from your transactional database association discovery. In your transactional database association analysis, the support is defined as a fraction of transactions that contain both X and Y. Okay? Use a ratio or fraction. Here, we actually define the support to be the number of documents. So this is the actual number of documents in the document database where those documents contain both the keywords in the left-hand side and the keywords on the right-hand side. That's the support. And certainly, you want your rules to have as high support as possible, meaning that these keywords are active, they are hot, they are frequently occurring in your documents, and they are important keywords. Okay? Confidence, the same thing. Okay? So the confidence for rule X implying Y is the percentage of documents in a document collection containing X that also contain Y. So the confidence for rule is exactly the same as the confidence for a transactional association rule. They have the same definitions. For example, suppose we have association, data implying mining, and suppose the support is 9 out of 10 documents. So that means out of these 10 documents, 9 documents contain the keyword data and mining. So the rule is data implies mining, or data determines mining. That's the rule. And suppose I say that the support of this rule is 9. That means 9 documents in my database contain both the keyword on the left-hand side of the rule, which is data, and also the keyword on the right-hand side of the rule, which is mining. And then I say that this rule has a confidence 90%. What I mean is that 90% of the documents in my database, okay, containing data that also contain mining. Okay, when a document contains data, then with 90% probability, that document also contains the word mining. Well, this is a little bit exaggerated. The data could be data management, could be data processing, could be data structures, not necessarily data mining. But because we are in the data mining field, we try to elaborate how important this data mining is. Okay. So 90% of documents that contain data also contain the keyword mining. That's how we interpret the confidence, 90%. So this is a formalization of this association rule, discovery algorithm for documents. I would like to, just leave this reading to you so that you can check this, and actually all the definitions are consistent with the definitions in the transactional association rule mining algorithm, particularly the a priori algorithm. I would like to just give you a particular example to show you how this algorithm works. Okay. So once again, I will post again the solution to homework 1 in the Web City, and also the solution to homework 2 in Web City today or tomorrow. All right? And you please go to the Web City, and you can find the links, and you can go there to download my solutions, and then you can read the solutions. If you have questions, please feel free to email me so that we can discuss. If you have questions about solutions and so on. Okay, so here's how we interpret the confidence. Suppose on the left hand side you have the keywords dog and a cat, and on the right hand side you have the keyword pet. And if 90% of these indexed documents containing the keywords dog and a cat also contain the keyword pet, then the confidence of the association dog cat implying pet is 90%. So that's a definition of this association. And how do you calculate the confidence of an association? Well, you find the support for dog cat, and then you find the support for dog cat and a pet, right? And then you divide, say you use the following formula. The support of dog, cat, and a pet divided by the support of dog and a cat. That gives you the confidence for this rule. That's how we calculate the confidence for association rules for transactional databases. The same formula. Okay? So that's the modification of the a priori algorithm. So actually, this transactional database mining or transactional association rule discovery was first published in 1995. 2 or 3 years later, a particular researcher from Israel, I think the name is Dr. I forgot the name, but he published this paper about text mining. So his observation is more important than his this innovation. He observes that there is a relationship between the modeling of transactions and the modeling of the documents. So he observed that, and then he can represent these documents just like keyword sets, and he can adapt the a priori algorithm to this particular domain. So he invented this field, but in fact, a lot of ideas are motivated by the a priori algorithm for transactional database mining. Okay. So let us look at a particular example. So this is an example association between keywords. Find all associations including gold and any country. So here's the result. You have gold, copper, that implies Canada. The support of this rule is 5, meaning that there are 5 documents in your database that contain gold, copper, and Canada. The confidence for this rule is 55.6%. Okay? That means 55.6% of documents that contain gold and copper also contain the keyword Canada. Okay? Gold, silver implies USA. The confidence is 69.2%. That's that's what we discover from a collection of documents. So let me move on to an example, a specific example. So in this example, you have a database of 7 documents. Okay? And these documents are numbered from 1 to 7. So the first document has a keyword computer stock. The second document has a keyword economy, finance, stock, and so on and so on. So this is very much like a transactions where each transaction contains a bunch of items. So any question about this input data? So that's the input of the algorithm. And suppose that we are only interested in those associations whose support is greater than 1. Okay, at least the support must be 2 or 3 and so on. Then, okay, so we generate 1 keyword set. That is, those keyword sets containing only 1 keyword. So these are 1 keyword set, very much like your 1 item set that you have learned in the past. Okay? So you generate these 1 keyword sets and you scan the database once to find their support. So the support for computer is 3, meaning that there are 3 documents in your database that contain the keyword computer. So let us check that. Computer, D1 has computer, D3 has computer, D4 has computer. So there are 3 documents containing the keyword computer. All right? Is that clear to you about how I find these support values for these 1 keyword sets? So once again, let me remind you that given a set of original documents, perhaps the most difficult thing for you right now is how to represent them by these keyword sets here. Okay, so you have to predefine a set of important keywords for your documents at your hand, and then for each document you check to see whether the document contains those keywords or not. For example, this D1 has only computer and stock, and D2 on the other hand has economy, finance, stock, and so on. And from these keywords, you relatively can guess what this document is talking about. This document basically emphasizes economy, finance, and stock. Nothing to do with sports and so on. All right? Any question about the algorithm so far? Then from these one keyword sets, you try to generate two keyword sets. So once again, you can sort these keywords in lexicographical order and then append these keywords one by one in turn. For example, you have computer economy, you have computer finance, you have computer management, you have computer stock. And then for economy, you append finance to economy, you get a two item set, right? Economy finance, economy management, economy stock, and then finance management, finance stock, management stock, and so on. That's how we generate two keyword sets. Okay? So these are all possible keyword sets. Two keyword sets. A two keyword set is a keyword set that contains two keywords. That's the definition. Well, after you get this, you have to scan the database once to find the support values for these two keyword sets. So these are the support values, okay? And then you erase those two keyword sets whose support values are less than 2, okay? So I erase this one, I erase this one, because they are not promised anymore based on the a priori principle. And then you have these promising two keyword sets. The next job is to generate 3 keyword sets. And once again, you can solve these keywords and you append these keywords to each 2 keyword sets one by one. So I get the following 3 keyword sets. And I scan the database again, I get the following support values. Okay. So I get the support values for these 3 keyword sets. And for those 3 keyword sets whose support values are less than 2, I erase them because the condition is that I'm only interested in association rules with support greater than 1. So this one is gone, this one is gone, this one is gone, this one is gone. Okay, so that's the only 3 keyword set that has a sufficient support. Then from here, I try to generate 4 keyword sets. There's no 4 keyword sets to be generated. I'm done. Okay? So from here, you can generate possible associations or association rules between keywords. For example, I can look at the combination, the following combination. Economy finance implies stock. For that rule, the support is 2, right? That's no problem because the support for the 3 keywords is 2. And then you have to calculate the confidence of that rule to see whether the confidence is high enough or, whether the confidence satisfies the user parameter value or not. Any question about this algorithm? If you don't have question, then you will, I should not say you have to, but I say you will practice this idea by doing the homework for text mining. Given a set of documents shown in the next transparency, find all association rules between keywords with the minimum support 2 and with the minimum confidence 80%. So that's a document database you have. So this homework 4 is very much similar to your homework 1 that you have exercises. Okay? And similarly, the implementation project 3 then is very similar to your implementation project 1. So my advice is that you build this implementation project 3 based on your implementation project 1. Most of the code is still applicable to this implementation project 3. I'm going to announce the due date for implementation project 3 in the web city. The goal of this project is to implement a web-based text mining system. You are given a website as, for example, you start with Dr. Wayne's website, http://cs.nji.edu/tutor.json. That's my website. And then from my website, your system will extract n websites reachable from my website, where n is a user-specified parameter values. So I give you a value, for example, 100. Then your system will automatically extract 100 websites reachable from my website. Okay? Now, in general, this is something that you have to think about. In general, this data mine, there's a website, is a graph. So start with my site. You start with my site and you try to find the sites that are connected from my site. But you have a lot of edges, right? And so my suggestion is that you use a depth search traversal of graphs to try to locate the sites that are reachable from my site. All right? So anyway, you extract, for example, 100 sites from my site. Each website is an HTML page. So you have to analyze these pages, and then you basically identify keywords appearing in these 100 websites dynamically. Okay? Because I might change the parameter value to 50, and you get another 50 documents, and this time the keywords will be changed as well. So these keywords cannot be predefined. They have to be identified at the runtime. You get these websites, you scan the websites, you collect the keywords from the websites, and those keywords are used to model these documents. And then, after you identify these keywords appearing in the websites at your hand, and then, so for each document, you can tell whether this particular keyword appears in that document or not. So basically then you have a database of documents, and for each document, it basically is a collection of keywords that appear in that document. And then you can apply the previous text mining algorithm or the association rule discovery algorithm to try to find the associations between those keywords that you discover. And then you should provide interface that allows me to enter the support and the confidence, where the support and confidence are specified by users. For example, among these documents and these keywords, I'm only interested in associations that have support at least 2 and the confidence 50% or 60%. And once I input these parameter values to your engine, you are able to display all the associations between keywords and present to me. Ideally, the system should run on the web and should provide interface that allows me or the grader to type in the parameter values, including the number of websites to be extracted, the number of keywords to be considered, and the support and the confidence, and so on. Okay. Now, the number of keywords to be considered can be, this number can be determined by your program. Okay, your program scans these HTML pages, and your program finds important keywords from these HTML pages, and then use those important keywords to model those documents. Any question about the project 3? This is so you see that we started with a simple project, standalone project, which is your project 1, to find the associations between items. Now we gradually move to web, but the idea essentially is the same. Okay, but right now you are going to post your system on the web and run your system on the web. Okay. Any question about this project 3? Okay, let me then stop here